good. Cool. So, hello everyone. Welcome to the next edition of Mython AI Times. Thank you all for coming and joining online. First things first. So today we will have a photograph present who will be taking pictures of the event. If you don't want to be in the pictures, just tell her. Her name is Paulina, right? Yeah, that's one thing. All right, if everybody's okay with it, then we can proceed. Today, it will be Martin Spišák from GLAMI talking about the SANSA model, which is a result of our cooperation with the Charles University. It's about recommender systems. And I know that he has prepared even a short workshop, let's say, or practical example of using the SANSA model. So yeah, there's going to be definitely a lot of space to ask questions at the end. But if you see something very interesting, feel free to jump in. Or if you're online, just unmute yourself. We can hear you in the room as well. So yeah, thank you. The floor is yours, Martin.
You hear me? Up? Yes. So thanks, Tonda, for the kind introduction, and welcome to this month's public Mython Times, where the theme is our little model that we named SANSA for some shortcut reason, and it's about recommendation, as Tonda said, and I will try to introduce you to the problem that we have here in our scale of data and recommendation tasks that we need to solve, and how we thought about that problem and created some solution that would work for our system. So I don't know about you, but when I'm not currently buying computers and computer mice and whatever, then I sometimes need to buy some clothes. And whenever I'm trying to decide what I want, t-shirt or shirt or something, I basically know that I want a shirt. And so I wouldn't even know what to ask somebody or some fashion attendant to what would I tell some person or some system that I'm interested in that sense. So that's where recommender systems come in. They complement search for people that know that they want something, but they don't know what they want, or they just would like to see something and tell you yes or no. And this is a very well studied problem. It started back in the 90s, and it started by recommending books in the library for people. And after some time, people understood that you could actually gain some business value from successfully employing these ideas in production systems. And over time, people decided that doing personalized recommendation, tailoring what every user sees to each individual's tastes is better. And this problem is pretty complicated because the tastes can change, and I would not necessarily like something that I like today a year from now. And so diverse and personalized recommendations are often better for people, and as the taste evolves, it creates a complicated problem. And sometimes we just want to be surprised and not even follow our taste. So the question is, how would something or someone want to model such a complicated question? And then consider our system where we are one of the, or if not the largest fashion e-commerce portal in Europe. We have, I think, 15 million products, over several geos. It's more than a dozen, definitely. We have some tens of millions of recommendations every month. Millions of users come and want to see some personalization from our website, and we also need to adjust for the tastes as they evolve over the time. So we need to retrain these models periodically, and we would need to create something that is scalable and be able to deliver these recommendations to these many users. We also track Web Vital. We don't want to slow down our system, so we need to infer very quickly. And I've listed here that we need to stay under 75 milliseconds median response time, and this is like the full round trip, like from when the user comes to our website all the way to some cloud where our machine learning is processed and the return response as well. And this needs to happen in the quick 75 milliseconds, because otherwise we would not be like rated high in the Google. PageRank would place it lower, it would worsen your conversion and business metrics and whatever. And on top of that, we have a really, really large turnover of items. I think it's like perhaps 20% of new items every week, maybe. This may be right, yeah. Like it's definitely thousands of new items and also users coming to our website every day. And we need to be able to recommend to people who we don't know, because you can opt out from cookies and just come as an as a completely new person to a website, and you would want to do 1, 2, 3 clicks and see something that's interesting and relevant to you, and be able to decide quickly and buy the stuff. And yet somehow we are able to do this task, which is kind of interesting. But right, so about a year ago, we decided that our current system is, I wouldn't say like obsolete, but it could be maybe improved, or we could try something newer. For example, there are many different types of recommender paradigms you could employ in such a large system, and collaborative filtering is one of them, and we use it and have used it in the past. And it's basically just learn what other people have liked, and if someone is similar to like these people or these items, then select something that matches these preferences learned. You typically have some sparse user item matrix that's just data that someone has liked this item, has no preference on this item, and has liked this item. And also you have some person that has liked this item, has no preference, or like doesn't like this item, and also there's some new item that he or she has not seen before. So the question is, would the person like this item, or would he not? And so this is basically what collaborative filtering is trying to solve, and the model predictions then predict the missing values in the matrix. And there are different methods, such as k nearest neighbors or alternating least squares here, and there are also some other approaches. But when you consider the scale of the task that I've shown here, that you quickly realize that you cannot really employ anything else than basically these methods. Maybe something else that is like really simple, but deep learning methods just don't scale. You cannot really train it for millions of items, because even taking 50,000 or 100,000 items would take you several hours, for example, which is a lot. And so the training the complexity can be very often quadratic in the number of items or so, and it just would destroy your budget at least. And so also inference time is very important. You can't have some like super gigantic, ginormous model somewhere and run several hundred GPUs for inference on the website of a e-shop, because that would ruin your budget. Right? So that's kind of sad news for the recommender system community, and people were trying to figure out something what can be done about this problem. And so luckily, there's been several simpler approaches over the years, and one of them, very notable, is the embarrassingly shallow autoencoder by Harald Steck. He's from Netflix. It's paper from 2019, so it's like really fresh. And surprisingly, he suggests we just focus on linear regression over the items. Like, what would that mean? Is that for every user, we would get basically one hot encoded item vector, and we would forward propagate this vector through this weight matrix and get some other rating vector for every item, and just these would be the scores of the system for this person. So like actually like this system then works by creating like an embedding of the item in some other space, that when you send one item through it, you get a bunch of other items that basically represent the same thing as the one item. And surprisingly, even despite it being just linear regression, it is capable of achieving even state-of-the-art accuracy on some data sets, or like very close to it on others, on pretty large scales. Also, since it's a linear regression, it's pretty simple to train, because you can use the closed-form solution for it, and you do not need to propagate any gradient. It's not basically deep learning. You just compute the solution of the regression problem there. And yeah, I've skipped the reasons for the high accuracy of the model, which I will return to after stating its high the problematic part of it is, yeah. So despite it just being a linear regression, even this doesn't scale to millions of items. And the reason is that we are computing a regression between, for example, 1 million dimensional spaces, right? So we would need to construct a matrix of a dimension with the number of items as its side. And this matrix is, even though the data for it is sparse, this matrix would get kind of more dense. But as you start to invert it to solve the closed-form solution problem, this will get like completely dense. And this is a numerical fact that which really nicely corresponds to this item graph displayed here, and also corresponds to the reason why the model is so powerful. Since it's a linear regression, it's the weight matrix is full rank. So one of the authors claimed that the high model capacity actually can be the reason for the high performance of it. But in my opinion, it's more of a side effect, maybe. The model's primarily strength is that it could identify some items that are related in the item similarity or relation network, despite these items not having direct connections between each other. And so what I mean here is, when you consider the user item network, which is just rewriting of this matrix, some users have some items that they have seen or rated or something. This is your data, and you typically do the collaborative filtering models by constructing the Gramian of this matrix, which is like an inner product through the dimension of users. And as you multiply this together, you get an item-item network where you have a direct edge between two items whenever there exists a common user that has seen both of them. And this is like if and only if statement. And this is what you would typically be able to see with like a item KNN network. You do cosine similarity, you get one item in this graph, and you ask what I can recommend to this user. So you can recommend whatever is directly related to this item and nothing else, and you don't see anything. But ease model, with it inverting the item matrix, the network corresponding to the Gramian, actually is able to find any item that is somehow related to this item through a chain of these interactions. It sees global interactions. And we know that this network is dense. Like the matrix is dense, which means the network is completely connected. And so you can actually reach, or like in a general case, you can actually reach every item starting from every item, which is super cool. Sometimes you can have a very long relationship between two items that would not be otherwise seen, like cannot be found for using the cosine similarity. And this network, if it identifies it as like a dominant relationship in the network, it could actually select the long distance item as a prediction for it. And yeah, so this is like the high capacity or like high scale of the search that the model is actually able to do in the graph, but it has to keep this graph in the memory somewhere. And this graph is large since it's connected. And so if we had a 1,000,000 item data set, the model would require 4 terabytes of RAM. And if you want to run an inference job on this, you need to put this in RAM, and I don't know, it's expensive. So yeah, we decided that we don't really want to do that, and so tried to think of something else. And so what we actually observed is you don't really need the dense matrix, as there are so many parameters for so few items in the space that it just doesn't make sense that you would ever need that much information to capture this model. And so it turns out you can actually pretty accurately approximate the dense inverse matrix by just keeping the dominant values of it. You can discard it and it would work basically the same. And this is like an exercise. Ease is a model that is 4 lines of Python code. And if you just add like 2 more lines to drop everything that's below 99 percentile of the model, or like the 1% of the dominant weights, for example, it turns out it would perform exactly the same. It's like strange, but it just makes sense that you don't really need so many edges between everything and so many paths between everything in the network. You can compress this network to something that represents the same thing. And this is what the dominant weights basically do. And so this is like a really easy idea that one can do. The difficult part is how you could actually compute it efficiently, because what I've said is, okay, so we compute the full ease and then just compress it and it works. But you don't have money, for example, to compute it sometimes, right? So so we would need something that is able to do it like reliably and stably and even pretty fast or cheap. And luckily it's possible, and this is what our model is about. We call it the scalable approximate non-symmetric autoencoder. It means that the model scales to large data. It approximates ease, which is an autoencoder, and our model is also an autoencoder between two large dimensional spaces of some representations, and it's non-symmetric, and it's because we have 2 different matrices. We use factorization in the model to enforce even larger compression, and by doing this, we are actually able to save space and just simulate what ease does with much fewer parameters. And how we actually compute it is relatively simple if you do numerical mathematics. Pretty out of the touch for everyone else in the world. So yeah, we just use something that's common in these circles of people, which is factorized sparse approximate inversion, which is a tool that people use to solve some iterative numerical systems, some large equations. And sometimes when you need to have these iterations stable, you need to precondition the system, and it converges faster. And this is one of the tools to make it converge faster. It transforms the original system to something easier to solve. And so since it needs to be employed in really large situations where people solve some like billion by billion matrices for some, I don't know, scientific purposes, and these purposes, the models have some structures in it, and this model needs to preserve this like the delicate relationships in the some structural data or patterns in there. Like really sophisticated methods needed to be developed in the sphere over, I don't know, like past 50 years, give or take. And these approaches are actually able to extract the dominant information from such networks. Like you can sparsely like sparsify the network, or like compress it in some way that the dominant parts of it are preserved, or like more or less preserved, and everything else you disregard because it's basically noise. And yeah, so instead of having one layer neural network, which is ease, we have a 2-layer neural network, and we train it in like 3 simple steps. We simply compute the approximate or incomplete Cholesky factorization, which is a decomposition technique used in mathematics. If you've never heard of it and want to learn about it, then just Google it. And there are very strong techniques for the sparse and incomplete factorization, because it's also a numerical tool that people have to use. And since they only use sparse data, it can actually be super efficient, by 1 order of magnitude more efficient, as in the number of flops, for example, needed to compute it. And so this would give us the decomposition of the matrix, but we need to invert it actually. So what we observed is that you can really cheaply get an excellent approximation of the inverse factor of one of the matrices by just changing the signs under the diagonal, because it just works. And I actually did some additional maths for it in my master's thesis recently, and it's a I don't know, like a curious fact of how these things works. But yeah, what we need to know is that this is often enough, and when it's not enough, we can just do some easy refinement of the product that is obtaining there. And once we do this, we get some inverse factor L here, and we just adjust it in the proper way and do basically whatever is does after it is done with the inversion, and we are left with 2 sparse weight matrices, and that's it basically. So whenever we need to infer on this model, we just run 2 sparse matrix multiplications. That's just linear combinations of some columns of or rows of the matrix. It's actually faster than full matrix multiplication, like a dense multiplication, because you often get only a few of these columns that you need to combine. So you also save time in inference. And so, as I've said, the approaches developed for it are robust, and it shows also in our experiments. The the table that is here on the slide actually doesn't reflect this fact like that great, because the data set is relatively sparse already, but we also tested on some like really simple recommendation data sets that are basically fully dense once you compute these XTX matrix here. This is dense, and so like it doesn't even really make sense to run this type of algorithm on the data, because you could more easily just compute it, in the standard way and then sparsify it. But like it works, like despite this being like tailored to it, it just works, And where it really shows the gains of the method is when you have a really sparse data. And like this data set has about 50,000 users and about 90,000 items, which is about 2 times larger than like the largest popular recommender data sets for the benchmarks, and about 4 times larger than like the most popular one. And they also have much less data in it, like much less edges in the user item network. So it actually turns out that when you compute this matrix, the XTX matrix, it's actually relatively sparse, not as sparse as, for example, our data when we have millions of items and a bunch of users that just do one interaction or so. But still, it's the best approximation that we were able to find in some like common benchmarks. And so using our method, we are able to like reduce the training memory footprint by 10 times compared to the best available approach, and by perhaps 50 times or 100 times on the data set compared to some like larger methods like ease, right? And it also turns out that we can train it several orders of magnitude faster than ease or other methods, and some like graph convolutions. You need a GPU for it and train it for an hour. And then we came in with a model that runs on a single thread and trains it in a minute. And yeah, also it's faster than the other competitor. If anyone is like curious about this, I can talk about it later after the presentation. For example, it's a similar concept to what we do, but the numerical idea behind it is like little older, or less tailored to the super sparse, really unstructured item networks. They do something that's more focused on some like local regions, and so it's like a convolution on the network. But yeah, I can tell you more about it later. And so the most important fact for us is that we can train faster, and we don't need as much memory as we would need with the original model. So here on this graph, you can see in green and orange is the best existing alternative to the ease method. And here in blue is our method, and the memory consumption difference is like pretty substantial. And if you were to graph how much ease would like consume memory for its computation, it would be like, I don't know, maybe it wouldn't even fit on this page. I haven't seen the graph yet. Maybe I'll just plot it sometime in the future, just for for smiles. And yeah, that was a relatively quick introduction to our method. We encourage you to look it up. It's on DL ACM, and it's free access, so or open access or whatever. I don't know how it's called. So we published this to the Rexis conference this year, where we were like successful, and we got awarded the best short paper runner-up on the conference. So yeah, please look it up, and if you have some comments, like reach out to us. Maybe you have some other idea where you could use the sparse inverse. I've heard that it actually is useful for some other tasks as well, and so maybe we can chat and yeah, reach out to us. And So right, the conclusion, maybe I don't even need to talk about it that much, but we just created a model that approximates the really globally capable model is by using some like novel sparse approximate inverse technique. And after doing this, we're able to construct a sparse linear autoencoder, which is able to capture these global item relations in the network. It's robust. It exploits the sparsity, so it's fast and memory efficient, and is able to scale the problematic part of the model to work, on millions of items. And last but not least, the model is actually open source. We've created a GitLab or GitHub repository, and please give us a star if you liked it, and follow for more. Right, and that's it from the presentation. But we also have a demo on Google Colab where we can see like what the model actually can do on the Amazon Books dataset I have listed there. So yeah, this Google Colab notebook will be later added to the repo, maybe today, tomorrow, it will be there. And it's a really simple, fast demo. I hope this is done. Yes. So we just installed some the requirements for the model here and download the repo, and then install or like import some libraries for whatever we will be doing later here. Then to train the model, you need to create a subclass of a dataset class, what we call in the repository. It's pretty simple. We here download the required data, put it where it needs to be put, and then construct a subclass of, I don't know where it is. Yeah, it's here. Right. So we just have a class created for this particular data set, because as you have different data, you need to like pre-process it differently. We did this the classes for it to correspond with the protocols used in the paper, and also that we would have easy time working on it, and like people could reproduce it easily. And so if you were to use it on your own data, you would need to implement something like this, or just take the model and toss out the trash that we put there around it. And yeah. So basically, once you have this like subclass here, you just instantiate it and call something called from config. It creates the dataset for you. I probably need to run this, and yeah, the touchpad doesn't work. So that's what you warned me about. That's on me. So yeah, this is downloading some data here. It's done. Is it done? Okay, so this right. So yeah, I now created the dataset instance. It's fast also, and I now created a function that, because since it's an Amazon dataset, we can actually map the IDs of the items to some like real Amazon IDs, and we can use these IDs to parse some images. So I will also run this, and then maybe this won't be that pretty to show, but we have some histogram of the data set. It says that it has about 90,000 items, with the least number of interactions being 10 for the data set, and about 2,000 for the most popular item. So we sorry about that. I want to show you the graph, but it doesn't want to let me. Yeah, so it's a typical recommender data set. You have a really long tail of the items that are not popular, and a few items that have so many interactions. And also something similar happens for the user part. here, oh, like, yeah, I have the most popular items graphed. It's some books that people like to read a lot, and yeah, I also did something similar for the distribution of user activity. It's also long tail. You have some bots here and some normal people, and yeah, whatever. This is not really important for us. The important part is here. Once you would like to use the model, you just create an instance of it by calling from config from the imported class of the model in a repo. You specify some parameters of the config. That's another great thing about ease and our technique as well, that the hyperparameters are really simple. You just have the L2 regularization, which is not even that important for ease. It sometimes works great, and I probably have not really seen it fail that massively. And you can specify the density of your resulting model. Maybe it's twice density, I'm not really sure, but you just say how many, how large your target model is, and you will get this sparse or this dense model from it. And then there are some hyperparameters for the approximate inverse, because as I've talked about before, we compute the L factor, we do some initial, the initial guess for it that actually works in most cases. Sorry. But sometimes you want to refine it a bit, so you can specify how much you refine it by selecting these parameters. This is, you can more coarsely go through the entire matrix several times. This is the first number, or then you can go through the entire matrix and only select the most damaged columns in each pass, and this is the second number of what you would do. And sometimes you could specify too big of a number and it just wouldn't want to stop, but once you have some reasonable loss threshold here, it will just stop the training for you. And yeah, and also you can specify two different decomposition methods. First one is ICF, and this is probably even more important. The first one is ICF. It's the incomplete Cholesky factorization, which works well on the super sparse data, and this is what you would typically want to use if you deployed it to some production setting. But also you can use the Cholmod method, which is some super well-written C library for parallel decomposition of it. It's really fast, but you need a lot of RAM for it. And I won't go to the detail, but it's more accurate on dense data than ICF. You can actually reach identical performance at high compression with it. And if you use ICF on smaller, denser data, then you would get some error in it. But once you go past, I don't know, 40, 50,000 items, it basically doesn't even make sense to use Chromod, because ICF already matches the performance, because the number of information that's extra in the data just is super large. So now I should just instantiate the model. Maybe something that's interesting, but yeah, Colab was having a hard time, I guess. And so yeah, we have a model ready and we can train it. So we just create some dataset split, standard procedure, train, well, test. From the data, there's some dataset split or create splits method in the dataset, which you need to also implement to do this. And this will actually take some time because it needs to do some inefficient processing on the data. So maybe if you have some questions, now it's a great time to fill some time. Yes.
Yeah. Good.
So just really quickly, I missed. You said there is the target density that you can specify, and so that comes into play during the factorization, during the matrix factorization, as part of the numerical process.
Yes. It depends on the factorization method that you use. If you use the Chalmod method, it just computes the dense factor, or like the complete full factorization, which would result in a denser factor, or like the denser weight part for you, and then you would use this to drop to your target, density of the model. But the ICF is like more clever in a way that it computes the factorization incompletely. So you already just take all your input data and you don't create any fill-in, as it's called in the numerical terminology. And like you basically don't care about generating fill-in, since every you compute each column sequentially, and then once you reach a column that's more dense than what you would like, you drop small values of it and just keep the largest part of it. And nice. So we actually were able to create the splits and now are ready for the training. So we are now training the Amazon Books model, which should take about a minute or two. So we have time for one more or two more questions.
Okay, just to be sure, is the model by design or designed to be always retrained from scratch, or is there some possibility of incremental training?
Right. So there are ease model is only possible to retrain from scratch, like the vanilla ease. But there are some like adjustments from like some follow-up papers that actually are able to do iterative retraining of the model that just focus on some low rank update of the inverse matrix. It's again some numerical technique used in the system. And yeah, so our technique doesn't support it. And I've been asked this question by the guy that was my the referee for my thesis, and I wasn't really sure what to answer, because the answer is probably, well, it's complicated. Like I wouldn't want to try it.
Okay.
Right. So yes, we are currently computing the incomplete decomposition, which first needs to look up for fill-in reducing permutation, because otherwise, if you would not permute the matrix, you would get a pretty dense L factor. But once you find a good permutation, you can actually save a lot of space by just not computing, fill-in factors. You factorize it more cleverly, and this is probably the most important part of the entire algorithm, because the rest of it is like pretty simple and actually would do basically the same every time. But this helps you save space and make for example, the incomplete factorization more stable. So if you were to not perform this step, you would probably fail the training miserably. You would need to add some more L2 regularization to the inverse to make it more robust. As there are some like inconsistencies in how you do like complete or incomplete factorization, and these would like result in breakdowns. You could get zeros on diagonal, and you can't do that because you need to divide by these values. And yeah, so we are done with training. It took 90 seconds. We have a model that's about 20 megabytes large. And now we are ready to evaluate it on this data set. So we just now import the evaluate method from the code we wrote. We selected the split as the test split. We want to evaluate recall and NDCG for some top top 20 and top 40 items, and we run it in some batch size. You can specify it. You don't really need to. It probably doesn't matter. This would just make it faster because it's better to compute matrix products than to compute vector products with sparse matrices, because you can actually vectorize it. You do some single instruction multiple data parallelism there. So yes, it is. Yeah, it's done, but I want to scroll down here. So can you see the numbers here? I can zoom in, maybe. Yes, this. So we were able to achieve something like, I don't know, 0.078 in recall and some 0.062 in NDCD at top 20 items. These, the metrics, like, in my opinion, don't really make sense this way. It's just some protocol to compute the value, and there are other ways to compute recall, for example, that is like more, it gives you better information about what kind of result you are getting. Because if you were to do it in the other way, you actually get results from 0 to 1. So it's a standard metric. Whereas here, it kind of depends on how many interactions the user has, and like if you recommend more items than the user has, and then you like ask how many of the 20 items I've matched for the user with one item, then you can only say one, and you would have like 19 incorrect guesses, and it's presses the metric down, doesn't really matter. But yeah, I just wanted to show you the number, and I also included the benchmark for this particular data set, which is what we also used in the paper. And as you can see, the highest recall, for example, here is the 0.755, where we had 0.078. So pretty nice increase over these top methods here, and it probably took a few hours to train this, and we managed to do it here while answering one question. So, yeah, So last but not least, I have some demo where we can actually look at what the item is able to recommend for people. And I've created 3 different setups for what you could expect. You can have someone with some standard taste. You would classify it as mainstream. They have probably like numerous interactions with something classic. This person, for example, likes Terry Pratchett, Stephen King. Like it's the pretty normal book taste, I would say. And so we just sample this user and like get their data, and we can look at their interactions here. So this is, I'm sorry, no. I need to zoom out again for it to make it work. So yeah, we have the user here with books like these. So as I've said, this is just some like random sample of their interactions, and we can like generate some more samples. Look at what it is: Stephen King, Terry Pratchett, whatever. And if we scroll down, we can specify the inference for the model, right? So we would want to recommend 20 items for this user. We simply generate 2 NumPy arrays with the interacted item IDs and the interacted feedback from the data. Tell the model to recommend the top K items, and then just some transform this to make the scores have some actual meaning. This would create the vector of generated scores to be a unit vector. So you could actually consider it a representation of the input items in some like latent space. And so if we generate this, it actually like recommends some other Terry Pratchett and some this Philip Pullman and Stephen King. It's different from what they've interacted. You can trust me, I've checked. I could show you, but I am scared of breaking down this notebook. So yeah, and we can see what the target items were for this person, which is just some subset of the training data, or like the test set for the test interactions. So from out of all the interactions the user did, we sample some, depends on what, for example, protocol you use. You can sample randomly, you can sample the last ones, which makes more sense, but I don't know what's used here. It's some fixed test set, and it's also this Terry Pratchett and something else. And I will zoom out even more to show you that we actually were able to get all of these books there, I think. So these are the three here, and the white here are actually all in this part. So yeah, that's the mainstream taste for a user. Maybe I'll skip this one since it's probably not that cool, but we can also look at what the model is able to learn for a long tail item, which would typically result in you having some random generated items because you have no information about it, because it isn't connected to as many items in the network. And so if we look at this, we can sample some long tail item, which is something like this. Sorry. Seems like some romance type book with 10 interactions in the data set. And so let's see what the model would actually tell you are the good matches for this. So if we infer for this particular input, we also get some romance books that are pretty, close, or like the genre at least matches. So it probably makes sense that it's not just some like random sports book or some like encyclopedia or whatever. Seems that all of them are some historical books or some romance books, which probably matches the genre. I don't know the book, so can't really tell you, but I don't know. It, at least to me, it makes sense that these recommendations are here. And this is randomly sampled, so I can like generate some more. Maybe we can, maybe we can't. Oh, this. All right. Yeah, I didn't implement some like PC filter for the demo, so yeah, maybe next year. And so we actually were able to find something that's maybe not correct, and we are probably going to get demonetized on YouTube. But yeah, if I don't know, maybe Tonda can tell me. Can I show this one more demo part, or do we want to cut it here and
I think we have like 2 more minutes, so yeah.
Okay, so let's try it. So this is a scenario where we have a user with small number of interactions. So above I've listed the users, descending, like in the descending order of how many clicks they have or like likes they have in the data set. And I've chosen some like random user from like the bottom 5 here, and it's this one. So once we generate it, we have 16 interactions, and if I remember correctly, they have 1 target item. So we create the input data in the form that we want, and oh yeah, this is the interactive data. So it's again some romance books. I guess maybe someone knows some of it, maybe they don't, because it's a 100,000 item data set. So if you know some of the books, you can correct me. But we have this for the input for the user and the sample of the input. And then we can infer from this. And it also finds romance books for this person. And it's great. It is what you would expect, right? So, and we can actually see that, yeah, this is what they would like to have the system recommended. And the book is here. So it works. Yeah. And I guess I can conclude with this more positive selection of books. And yeah, thank you everyone for coming. Maybe Tonda wants to say a few more words.
I think we should thank Martin, right? And yeah, we have some space for a couple more questions if there are any. If you're online, you can just unmute yourself or post into chat. Yeah, we already had a couple, right? So I wanted to mention that, yeah, if you're in person, there is going to be pizza and beer in a little while, and we can continue talking there, right? Martin is going to be here. And I also wanted to mention a couple of the things about organization. We will have, of course, next edition of Mid-on Times in about a month or two. We don't have the topic yet, but we will announce it, you know, as usual on Eventbrite, on Meetup.com, and we will upload the recording of this talk to our YouTube channel together with the slides and the Collab notebook, so everybody can find it easily, hopefully. And I think that's it for the organization. All right, so, you know, again, thank you, Martin. Thank you, everyone, for joining us. Yeah, see you next time. Yeah.